All right. Welcome everyone, and thank you for joining me today in this new webinar. I think we are all ready to get started. So before that, I just wanted to point out that if at any moment during the course of this webinar you have any questions or any comment, any suggestion, please feel free to send your questions through the chat, and I'll be happy to answer them. All right, so today's topic is based on the pedestrian wind comfort type of analysis that SimScale is offering, and we're going to analyze the effect that buildings have on these pedestrian comfort criteria. All right, so a bit before we get started, a little bit about me. So my name is Arno. I'm a technical marketing specialist here at SimScale. So I work extensively on the NFEA project, specifically for the architectural and construction engineering sector. And I've been working for the past few years as a mechanical design engineer using this type of tool to optimize and validate designs. All right, so a bit about SimScale first. So we've been founded in 2012, and we have offices in Munich, in Boston, and in New York. We are constantly growing, and we're over than 80 employees across the different time zones, and we have a huge community of users, and also a lot of public projects that you can use as a base for your own simulation project. All right, so what does SimScale do? So SimScale is an online platform, which means that you can access your simulation project through any web interface. This means that you can access all types of simulations. Could it be fluid dynamics, solid mechanics, or thermodynamics, all into one project. So you don't need any hardware, or you don't need any specific type of machines, and there's no real limitation in terms of the size of what you can simulate. And this is what I'll be covering as well today. All right, so today's application concerns the aerodynamics of buildings. So what we're going to do is we're trying to analyze the comfort criteria in an urban area, and trying to see what is happening at different zones, and trying to observe the result and discuss them afterwards. So this is essentially a three-part process. So we're going together to set up and run a simulation, which is called pedestrian wind comfort, or PWC if you prefer. And after this, we're going to analyze a first type of result that is called the Lawson criteria, and we're going to target and to observe any specific zones in the region that we've selected for the simulation, the zones where there's a high discomfort of people, and from these zones we're going to see what is happening and why do we have a discomfort at this particular location. And to do this, we're going to see a directional result in terms of velocity, especially taking into consideration the predominant wind in that particular area. So from that, we're going to draw some conclusions and make a comment out of these specific findings. All right, so I've been talking about wind comfort, but first of all, I want to explain a bit what do we mean by wind comfort. So wind comfort essentially are different, they correspond to a subjective, I really want to insist on the fact that it's a subjective feeling that individuals observe under certain conditions and under certain type of activities as well. So there are different type of comfort criteria. This is an example that you see on the left-hand side. And we go from different levels, from an activity type of criteria, which is acceptable when you want to read a book or when you're sitting somewhere, into more severe type of discomfort. until we reach a point where we're exceeding the uncomfortable zone and we enter a zone where it's not only uncomfortable, but it becomes an unsafe type of criteria. So this is important in the fact that it impacts not only like when you walk somewhere, it also impacts the how busy a street can be. If people can avoid some areas, if people avoid special terraces, or if there is like parks that are completely unused because there's so much wind, we don't want to sit there. I'm also thinking about safety as well, not only pedestrian safety, but also if you're riding a bicycle, for example, and there's a big gust going your way sideways, that can be very dangerous, actually. All right, so we're talking about wind criteria. So as I said, it's a subjective feeling, and it's also depending on the type of activities people are involved with. So there are different types of criteria. There are different criteria called Lawson, Davenport, NE, and 8100. And this defines different thresholds and different activities as well. So you can read more about this in the blog post that we're regularly publishing, and inform yourself more about this different criteria. All right, so let's take an example. So today we're going to take the example of, we're going to take an example and we're going to assess the pedestrian comfort in a specific urban area. We're going to use a year-round meteorological data, which means that we're going to collect data from a third-party supplier. This data, it concerns the direction of wind and the frequency of this wind, and in each direction. So this gives you a real realistic input into our simulation. From then, we're going to identify areas where it's uncomfortable for a specific activity. And we're going to investigate, okay, why is this uncomfortable at this particular location? And we are going to see different phenomena. It's going to be very interesting to see also visually what is happening. From then, from what we will observe, we're going to discuss how we can minimize these effects and how we can make the environment for pedestrians more comfortable and most of all more safe. So today I've decided to use the city of Paris. So this is more specifically if you're familiar with the district of La Défense in Paris. So I took this this model because I found very interesting the specific layout of this particular part of Paris, where we have high buildings, but they are quite close together. And you'll see that it creates quite interesting flow phenomenon. And also you can recognize, of course, the very iconic arch in the middle of the of that chart. Okay, so what we're trying to do here at SimScale is bringing you a simulation and making you run successful simulation in the most accessible way, in the simplest way possible. So we're trying to really simplify the setup and really narrow it down to what is the most important to you in terms of your input. So first of all, we create in our model, so in the model of Paris, we'll create some sort of disk that represents our region of interest. And we're then going to define, as we discussed before, the meteorological data. So we can input this kind of data into our simulation. And then we want to specify where we want these results to be. So at which height, so generally at 1.5 meter height, which is the pedestrian height. So from, let's say 1.5 to 2 meters height, but you can also set them up on terraces or on different heights. So I'm going to quickly show you on the platform what it looks like, and you'll see how simple it is. All right. So I hope you can all see my screen. So you can see that I have imported my model, and this is a STL type of file. What I can do then is I can click Create Simulation, and we have the option here called Pedestrian Wind Comfort Simulation. I can click Create Simulation, and this creates a new tree in my simulation tree. You can recognize instantly that we've automatically pulled out a region of interest to which you can change the radius, for example. I'm going to put 650. And this, of course, impacts the size of your results and how spread out your results are going to be. I specify the center and also the specific height. This is my 0 ground level. So you see on this particular example, I don't have a particular topology or terrain, but you can definitely include that if you are in a mountain or a more hilly region. But for this specific example, I haven't included. All right. So once we're happy with the region of interest, I can go onto my wind condition, and this is where we're going to input our meteorological data. So I'm typing the location, so by default in here, and we can automatically import our wind data. So this is a new feature we've implemented a few weeks ago, and directly you click here and it would pull out instantly from our third-party supplier. We're going to see our wind data. So this represents all the directions and the intensity of the wind at each direction. So first of all, we can see most predominant wind from southwest, south-southwest, and south. The third step, as we mentioned before, I'm going to select the pedestrian level. So when we don't have terrain, I can use the 0 floor and offset it to 1.5. That's all I need to do. Just like this. Okay. And now we're actually ready to go. This is as simple as this. So you don't need to modify anything else. I can just go to Simulation Runs and play. Press button. And I can click Start. I'm not going to start it right now, but this is essentially how simple the process is. All right. So let's go back to our presentation. Let me know if something isn't clear or if I'm going too fast on some ideas, and I can answer. I can come back to things. All right. So once we've run this project, here's what we have. So you can recognize that. So at this specific location, we see here between the buildings, we have red zones. So this means that we are exceeding a certain threshold and we are entering an uncomfortable area for pedestrians. And you see that with the right alignment, we can see that with the predominant winds from south, southwest, and south-southwest, we are aligned with these narrow passages. So this already tells you about something that is due to the presence of the buildings being very close to each other. We can see another areas a bit aside from the first one, where we have a big patch of uncomfortable zone. So let's see what's happening. When you run a simulation, pedestrian wind comfort simulation, you don't only output the wind comfort criteria map as you saw here, but for each direction, you can actually output at the pedestrian level that we've defined. You can actually output the velocity distribution in every direction that we've set up at the beginning. So all these directions are computed in one single simulation. So when I press new run, I have all my 16 directions computed at the same time in parallel. And this is the major benefit of using a cloud-based platform. So these directions, we are establishing 3 passes of the wind. So the wind goes 3 times across that that domain until we're seeing a developed pattern. So we really want to make sure that the simulation is accurate enough to output something that is realistic and meaningful. Okay, so what do we see here? So we see that for our predominant wind directions, we have you see that at the center we have really high wind velocity. So as the wind enters this region, it kind of accelerates to get its way through the buildings. All right. So these areas of high velocity are essentially created or high uncomfortable situation or location are actually connected to high velocity. This is what we saw. And these high velocities are created as an effect of the wind. So let's find out what this wind effect, what we say about wind effect, what it means. So there are different wind effects generated by buildings. They are not all equal and they don't have all the same effect. But what we have is, as a first wind effect, is the downwashing. Downwashing happens when you have a high and tall building surrounded by lower buildings, and you will see the wind going downwards as it approaches the facade of the tall building. The second one is what we call the channeling effect, and this is where 2 buildings are really close to each other, for example, in some narrow street. And you will see the wind accelerating to make its way through the buildings. The third one is what we call the corner acceleration, and this is what happens when the building reaches the edge, the vertical edge, when the wind reaches the vertical edge of tall buildings and accelerates as it passes through these edges. All right. So what does that mean? Now let's find out in terms of our specific example. So left-hand side, we are from the southwest direction. I've output our results from southwest, and you see that for the corner, we see that we have a high corner acceleration. We see the velocity really increasing as it goes through the edges of our building. You see on the right-hand side this nice animation where we see the streamlines, where the flow path accelerated becomes it reaches velocities to 6.5 or 7 meters per second as it goes around the building. So this is one first effect that that creates high velocity and creates therefore high comfort for pedestrians. The second one that we saw is channeling effect. So this is also happening in your wind comfort criteria map. And in the red zones, we see that these 2 blocks are really close to each other. There's a narrow passage between them, and this creates really high acceleration. You see that the fluid really wants to go through this narrow passage and accelerate. So that's a perfect example of this phenomenon happening here. This is what also called in a more general term, it's called the Venturi effect. All right, let's continue into our last one, and I found this a very obvious example of this downwash effect. So we see that we have a high and tall building here, but in front of it there's a lower building, and this makes the wind to go, the airflow to go downwards and accelerate as it reaches the floor. And this you'll see that creates really high velocity at lower altitude. And this is a really obvious example, and it is something that architects or urban layout managers and all these professions involved in this sector will have to take into consideration when they design a new building. This kind of simulation is extremely beneficial to really anticipate this kind of phenomenon. We've seen many times existing buildings, and they create a lot of discomfort. I invite you to check out our blog post or to check out our YouTube videos where we discuss examples where this is really happening, and somehow this could be prevented or could be mitigated with certain measures. All right. So talking about mitigating this effect, there's a couple of things that we can put in place. So depending on the stage of the building, is it already built or is it under development, we can create different features to prevent this. So what we see here, for example, we can install canopies to really counter the downwash effect that we've seen just before. This kind of shields the wind to enter entrance of buildings, for example. To also avoid placing entrances at the corner of buildings to avoid, obviously, the cornering effect. What's happening sometimes, we see that buildings have some kind of bevel at the vertical edges or have more rounded corners, and this is also a good way of preventing this kind of cornering effect. All right, and also what we can do is plant trees, which is also good for the environment, and which can have different effects. So shielding a certain area, and this is really useful for parks, for example, but also redirect the wind stream. What we can do if this, in the case of setting up a layout, is orientating the streets so that they are not aligned with the predominant wind. And that is also very obvious when you run this type of simulation, that when you have streets that are not aligned, you'll see lower velocities. All right. Yes, I think that's pretty much it for what we're covering today. I'm really happy if you guys have questions, or if you have any comments, if you want me to go back onto something else and yeah, just let me know if you have any questions and comments, and I'm happy to answer. All right, very interesting questions we have. All right, let's see. So how the CFD simulation result are validated against experimental wind tunnel data. So this is what we're trying to really show out there, is that we have taken different case studies, one of which was led by the Architectural Institute of Japan, and which has publicly exposed different wind tunnel data and actual real-life measurements, and we can correlate our CFD results with their results. So you can access this kind of study where we compare experimental data with our CFD results. All right. Another question: how long is the simulation? So we are setting up a multi-directional wind simulation, 16 directions at the same time. And we're using an LBM type of solver, which is particle based, and this allows us to be very efficient in the way the simulation is computed. But for this particular example, I'd say it took 2 to 3 hours for a very coarse pre-study, but you can go a lot more into a higher resolution and have a better definition of our wind comfort map and velocity map. So I'd say 3 hours, 2 to 3 hours, depending on how big your region of interest is as well. Is mesh refining needed? So this particular simulation used the lattice Boltzmann method, as I said, and which we have implemented an automatic kind of meshing algorithm behind the scenes to really highlight and really refine the areas of interest. You can obviously refine it manually. There's the option to refine in terms of region or refine it in terms of service. Thank you very much for all your questions. I hope I have time to answer all of them. We have a few questions about dispersion of air pollutants and passive scalars. This is something we are looking extensively to develop. It's going to come very soon with this type of analysis. You can already use passive scalars, but in another type of analysis, for example, the incompressible study, but this would use not the lattice Boltzmann method, but it would use the finite volume method. But this is also possible with SimScale. Oh, there's another question actually. Can I get force results on buildings? So this is something I haven't shown you there, but we can use LBM simulation to also output force plots on building facades. So you can monitor the pressure forces on particular locations. So you can select the face before you start the run, and it will compute an average force on the specific face. Yeah, that is correct. So what we can do for the input, you actually only need to input your what we call the ROS, the wind ROS data. So this is essentially telling you the frequency at every direction and the intensity of the wind at each direction. And this is all you need for the from the meteorological supply, which is the third-party supply. What you also need to input, what you can input, and I haven't shown you there, but you can define for each location, you can define what type of terrain you have upstream. So that means that if you have a very high, tall buildings next to the area of interest, you can also select this as a class of or category of terrain, and this will impact the results obviously because the wind velocity profile will be different. So you also have to, if you want your simulation to be more accurate, to input this kind of information. Can we use SketchUp models? So yes, you can use a lot of different CAD software to as an input for this simulation. You can use a lot of different formats. So SketchUp allows you to export your model as an STL, which is 100% compatible with this type of simulation, this type of analysis on SimScale. So using SketchUp is a good tool to prepare your geometry. You export it as an STL, and then you can import it onto SimScale. The model of turbulence that is used by default here for this LBM simulation, we have used a large eddy simulation for this one, but you can select a different turbulence model. Unfortunately, we're not there to the DNS type of simulation, as it will require a huge amount of cells, even already a lot larger than this one. Because for this type of simulation, we have approximately 9 million cells, which is already quite significant. We can go as high as 50 or 100 million cells, but yeah, this is the order of magnitude in terms of the computation. All right, I have an interesting question concerning the pedestrian wind comfort level. So these are essentially defined by standards. So we've seen we have Lawson criteria, NEN 8100, sorry, and Davenport. So I believe they are created on the type of activity, also on the region. So depending on where the company is based, they would adopt different criteria. You will see that some criteria are more conservative than others, which means that for the same results, you will have different maps. So one standard will tell you that it is comfortable, and the other one will tell you it's unsafe. So it's a very subjective way, and this is decided by the company itself to really select the right one. Yes, I'd like to thank you all for all these questions and for your attendance. And it was a pleasure for me to be here, and I hope you learned something. And I hope I'll also see you in the next video that we're going to release soon. And I wish you all a very nice evening or a nice day, depending on where you are in the world. Thank you, and see you in the next video. Bye.